Okay. Hi everyone. Good morning. How are you all? Hello Arnav. Hello Vani. Hi Sandeep. Hi Yuvraj. So I hope everyone is good. Okay. Now you people might be thinking कि ये सुबह सुबह linear algebra पढ़ना पड़ जाता है. But don't worry. It will be useful only. Okay. So today we are even going to start a very interesting topic, which is determinant. And we will build the theory about the determinant, how to drive the formula. I will not tell you the formula directly. We will build up everything from the scratch. Okay, so it will be quite interesting. Now this is completely a new chapter. The first chapter that we have already studied was the system of linear equations. Okay, so which is ax equal to b. Solving, let me write like this way. Maybe this was the chapter 1 where we have studied solving ax equal to b. Now we are going to start a new chapter, which is determinant and eigenvalues, eigenvectors. Okay. So in this chapter, all matrices are going to be square matrices. Here we will not talk about a m cross n. We will talk about a n cross n only. Which means all matrices are square matrices, means that number of rows and number of columns are actually same. Earlier, this could be anything. Earlier, it was a general matrix, which is A m cross n. But the determinant, eigenvalues, eigenvector, these things are defined only for the square matrices. So we will talk about only for the square matrices in this particular chapter. Okay. So let me start with determinant, and then in the next lecture we will be moving towards the eigenvalues and eigenvectors. So in today's lecture, I want to finish this determinant and inverse, like how to calculate the determinant. You might be doing it, but let's just look at determinants from the very scratch, like as if you do not even know anything about the determinants. Okay. So determinant of any matrix that is given to you, let's suppose A, and I say that we can calculate determinant of A, which means there is A is a matrix, and if I say that we can calculate determinant of A, then there is a scalar that is associated with the determinant, associated with this matrix. So this determinant of A is scalar, just like rank of A. If you remember, rank, it was also a scalar. Just like that, determinant of A is also a scalar. So rank of A tells many things about A, like number of linearly independent columns or rows, or like just a one number. I mean, just one scalar is having many good information about the matrix. Similarly, the determinant also has many good information about the matrix. Just this is the maximum thing that you can have in just one number, in just one scalar. Similarly, for the rank, determinant is just another one scalar which is very important in the matrices. And then we will move to the eigenvalues, eigenvectors. Then eigenvalues are again scalars, which tells many things about the matrices. So these are the few things that are for a given matrices, we can calculate these few things, and these few things are very useful to know few properties about the given matrix. Now, as I said, determinant is determinant of A is a scalar, and we will be calculating this determinant based on some properties. So, before I give you a formula of determinant, or how the determinant look like, let me tell you few properties of the determinant. And these properties are to be taken as it is, which means like there is no proof of this property. This is just given as it is. Like, okay, this is the property of determinant, like that. Okay, it's just like a function. I mean, you might have studied function. So you are basically applying a function over A, and then you are your output of this function, you can say, is an scalar. Which means, like in the function terminology, you can say that it is a function that goes from set of matrices, maybe I don't know, maybe let me just write M, which is a set of matrices, to a scalar, maybe real numbers, or real numbers in most of the cases. If the matrix is real, then it will be a real number only. Anyway, let's not talk about it. Let's directly go to the property. Okay. So first property says the determinant of n by n identity matrix is 1. Identity matrix is a matrix which is having diagonally 1, and it is obviously, see, in this chapter, as I said, everything will be a square matrix. Okay, in this chapter all matrices are square matrices. Now this matrix is a square matrix, then only I can calculate the determinant. And if it is an identity matrix is a matrix where you are having ones on the diagonal and everywhere else you are having zeros. So if it is identity matrix, then the determinant of that matrix is 1. It could be any size, maybe 2 by 2, maybe 3 by 3, and in general, it could be n by n identity matrix. Okay, this is just one property of determinant. I hope that is fine with everyone. Now, let's go to the second property. Second property says that determinant changes the sign when you change two rows, which means if this is one row, this is another row. And from this property 1, I know that this is 1, right? From the property 1, I know that this is 1. Now you might ask me that how to prove this property 1. Now my answer is that there is no proof of these properties. I will tell you 3 fundamental properties, and then based on that we will build some theory. Okay, so just take this 2-3 simple properties as it is, and then based on that we will build some formulas. Okay. Now property 2 says that if you exchange the rows, then it will tell you that the determinant of earlier, let's suppose it is 1, then if you exchange the rows, then the sign will get changes, then the sign will be -1. You can even exchange the columns. I will talk about this later. Okay, so you can, whatever you can do with the rows, you can also do with the columns in case of determinant. Because I will tell you about the later, but I'm just giving you the spoiler, which because determinant of A and determinant of A transpose are actually same. So whatever you can do with the rows, you can also do with the columns in case of determinant. Okay, let me know if there is any doubt here. So what I'm saying here is that if you change the rows, the sign will get changed. That's all I'm saying. So if you change these 2 rows, then sign will also get changed. Okay. Third property says that determinant is linear in the nature, which means that suppose you want to calculate the determinant of this, then you can write this as a determinant of these 2 matrices, which means you can apply the linearity. So linearity is 1 row at a time, which means that if that is the row, then you can write this row in this way, A B, and this row, like all other rows will be same. Okay, and then you can write this this row, this particular row, 1 row at a time, which is AB plus A bar B bar, which means, let's suppose if I say that there is a matrix which is A B C D E F G H I, and probably let's suppose I say this is plus X plus Y plus Z, then can you rewrite it? Yes. How? You can say that this is equal to A B C D E F G H I plus X Y Z D E F G H I. Okay, which means you can apply the linearity but 1 row at a time, which means for this row you can write like this. Okay, it will get clear. Let me ask you one question. Suppose you have this. Let's suppose you have this A plus B, A B, let me say A B C D. Let's suppose you have something like this, plus P plus Q plus R plus W. Can you write like this? A B C D plus P Q R W. Can you write like this? Tell me. Just based on the property, that we have just seen. No. Reason being is that because you have to write like, you have to apply the linearity, but 1 row at a time. You cannot apply the linearity 2 rows at the time. This is wrong. Then what is correct? You can say that this is same as A, B, but C plus R, D plus W, and then plus P, Q, R, C plus R, D plus W, which means that you can say that you can rewrite like this, but all other rows will be same. All the rows will be same. Only the first row or any row for that matter, you can apply the linearity. Okay, then you can further extend this, and then you can further say that this is nothing but the first term is nothing but A B C D plus A B R W. This is the first term, and the second term is nothing but P Q C D plus P Q R W, which means there will be 4 terms. But if I just write like this, then there are only 2 terms, A, B, C, D, and P, Q, R, W. This, like, these 2 terms should be added in this, then only these 2 are equal. Okay, I hope you're getting. So don't worry, we will do many examples, and after that it will be more clear. But for now, just understand like this, that if you have any row, then you can apply the linearity on that row only. Similarly, you can take the common in that row only. Okay, which means, I mean, if you look at this in this way, if you want, then you can look at this in this way also. Maybe this A, B, C, D plus A, B, C, D t times. Okay, t times, if you want, you can look in this way, but yeah, that is okay. I mean, you just take t common. I mean, let's have this way to look at this problem. You can take a t common, but from just one row or one column. Okay, you cannot take t common, which means if I ask you this, let's suppose t, maybe I have ta, tb, tc, td. Can I have like this equal to t a b c d? Is this correct? Answer is no. Reason being is that if you if you apply the linearity, then you have to take t common from one of the row, any one of the row. Maybe AB, let me take from the first row, and then you again have to apply the linearity, which means you again have to take t common, and in this case it will be t square. Yeah, it will be t square ABCD. Okay. So I hope that is fine. So which means this is incorrect, but yeah, this is correct. This is correct. Now let me see if there is any doubt. Nikhil is asking, can we write AC? 1 second. In this case, right? Can we write A, Y, C, and X, B, Z? Yeah, anything. Obviously, it is commutative. I mean, this A plus X and B plus Y and Y plus B, and these are same. Right? If you want, you can write B here, you can write by here, does not matter. Yeah. Okay. Okay. Veer is asking, so a scalar get multiplied to each element of the matrix. Right. Okay. So there's a nice observation. So Veer is saying that suppose if you want to multiply any scalar, let's suppose if you want to multiply 2 to a matrix. See, this is a matrix. This is not a determinant. If you multiply 2 to a matrix, let's suppose it is A, B, C, D, then it will be 2A, 2B, 2C, 2D. Okay. In the matrix, you multiply everywhere. Or in another way of saying it is that if you have a matrix like this, 2C, 2D, if it is a matrix, if you take a 2 common, then you need to take 2 common from everywhere. In a matrix, you need to take 2 common from everywhere. But in the determinant, if that is the story with the determinant, then you have to either multiply in one of the row or one of the column, or you have to take common from one of the row or one of the column, which means that let's take the first case. 1 second. So let's take this case. So in this case, you will say the determinant of this will be not this. Determinant of this will be, let me erase this, maybe this. Okay. In one of the row, or maybe in one of the column. I mean, this is also same as you can say 2A, 2C, B, and D. In one of the column, you need to multiply in one of the row or one of the column. And similarly, if you ask me that if you take the 2 common, then you need to take 2 common from one of the row, one of the column, maybe from this column. Okay, you are taking 2 common from this column. But earlier it was not the case. Earlier, if you are taking 2 common, then it has to be taken from every row and every column if it is a matrix. But this is not a matrix. This is a determinant. Okay. Okay, tell me if this is true or false just based on 3 properties. So what are those 3 properties that we have seen? First property is that determinant of identity matrix, which looks like this. Determinant of identity matrix is 1. If you exchange any row or any column, maybe let me exchange a row in the above matrix, then the sign of the determinant will get changed. So it will be -1. Third is linearity. Linearity means that if you have A plus X, B plus Y, C, D, then you can write it like this, maybe A, B, C, D plus X, Y, C, D. or if you have a T, then you can write like this. Maybe let me write here. 1 second. If you have something which is, let's suppose, T A, T B, C D, then you can write, you can take T common, it will be A B C D. So these are the three properties that we have seen. Now, just based on these three fundamental properties, we are going to build the formula, okay, for the determinant. So before that, let's have some practice. Let's just solve this question. Whether this is true or false, just answer using only property 1, 2, and 3. So obviously this is false. Reason being is that you are applying the linearity, you are not applying the linearity correctly. This is the correct way of putting this in the words. So you're not applying the linearity correctly because as you can see that you are applying the linearity, on more than one rows, which is not correct, right? Okay. Karthik is saying we have used determinant in solving Ax equal to B. Where we have used, Karthik? I think we have not used determinant yet, right? Okay. So this is false. Everyone got it? Okay. Now, tell me whether this is true or false. Based on these three properties only. Do not apply anything else. Whatever you know, that is good, but do not apply this. Is this true? Yeah, because everything is same, right? See, these rows are same, and then you are applying the linearity in one of the row. So you are saying that you are applying the linearity in one of the row. Okay. I mean, linearity does not mean that determinant. See, this is another way of writing DET, or sometimes I write like this. Sometimes I will write like this. I hope that is fine with everyone. Okay. So, like depending on the situation, I mean, there is no situation. Depending on the maybe mood, you can say, you can write in any way. Okay. So this is, let's suppose, linearity does not mean what I mean to say. Linearity does not mean this. I mean, linearity does not mean that these two determinants are equal. In fact, these are not equal in general. Can you give me some example? Maybe you can have some example here. Let's have A, which is having determinant 0. Maybe you can say 0, 0, 1, 1. And let's have B, which is also having determinant 0. Maybe 1, 1, 0, 0. And if you add A plus B, then it will be 1, 1, 1, 1. So anyway, we will talk about how to find the determinant. But yeah, if you find the determinant of A plus B, it is not 0, but this is 0, this is 0. So in general, that is not true. And this is not the linearity also. Linearity is applying on the row or on the column. Okay. Let's see this, if this is true or false. I think, can you answer me quickly? I think this is true. Okay, this is true. Which property you are applying? Property 3, right? I think we do not need anything else. So using property 3, you can say this is true. So you just need to use 1, 2, 3. You do not need to use anything else. Whatever you know, that is good. But let's just use only either first property, second property, or the third property. Okay. Okay. Tell me whether this is true or false. This is clearly false that we have seen. Okay. Now, tell me this is true or false. Which property you are applying? Here, you are applying 1 and 3. Yeah. You are applying 3 to take 2 common 2 times. And then you are applying property 1 to make it 1. So that's why the final answer is 4. Okay. From here to here, you are applying property 3. And from here to here, you are applying property 1. Because the identity matrix determinant is just 1. Okay. If 2 rows of A are equal, then determinant of A is equal to 0. Using property 1, 2, 3, answer me. You might be knowing that this is true, but why? Why that is true? Using property 1, 2, 3, answer me. Can anyone do this? It is little interesting. Using just property 1, 2, 3, you need to answer. No, do not apply any rank and all, okay? Just property 1, 2, 3. Apply one how? This is not an identity matrix. Okay, I will take A common. I will take A common and I will take B common, and then it will be 1, 1, 1, 1. Then what next? What I have to do next? Linearity. Okay. So, okay. So for the linearity, let me find out this. Maybe let me just say, I mean, maybe you can do it in that way, or maybe some other way. I mean, how to apply linearity? I'm not getting you. So if you apply linearity on this row, then you will be getting GP. Nikhil, or anyone, please do not suggest me any method that is not using property 1, 2, 3. Nikhil is suggesting me to subtract one row that you might be knowing, and Veer is suggesting me the same thing. I think you please keep that to yourself for now. Okay, we will come to those points. Just apply property 1, 2, 3. What I'm saying, do not apply anything else. You obviously you know that this is 0. I mean, most of you might be knowing it already, but just use property 1, 2, 3 and prove it that this is 0. This is the exercise. Okay. So Yuvraj is saying ki swap linearity and then swap rows and columns. That will be minus of the first. Okay. You are, I think, quite close. Identity matrix, how you are able to create using linearity? Identity matrix, how you are getting the identity matrix? That's only I'm looking for. If you apply the linearity, then I think we are not able to get the identity matrix, right? Take the first A as common. The ये तो मैंने कर लिया ना, A B तो common ले लिया, right? And once you get this, you need to prove this is 0. Then only ultimately things will be 0. You need to prove that this matrix or this determinant is 0. How you can do it? Ekta is having some idea, which is basically saying that exchange these two rows or columns. Okay, that is good. So I think that should work. So let me tell you how. But don't take column first. Okay, let me just try it. I'm not sure if you mean the same, but that is okay. So let's just try to prove that this is 0. Okay, that's very simple actually. Let's just say that you do not know whether this is 0 or not, and let's just say this is T. Okay, what you do, you exchange two rows, maybe this first row and second row. Then you will say that whatever you are getting is actually minus T, because you have exchanged, right? So this matrix, you believe it or not, I have exchanged. Okay, so I have exchanged first row and second row. Now this is minus T, and this is T also. You do not know whether this is 0. Let's not worry about whether this is 0 or not. You have exchanged first row and second row, you got the minus T. Then what you need to do, then you can say that some quantity which is T also, which is minus T also, then it must be 0. Or you can just add it and then you can say that this is 0. But from here also directly you can conclude that the determinant of A, B, C, D, or you can add these two quantity if you're not able to visualize directly, it is 0. Then, I mean, after adding, you can add these two equations, right? This is just a scalar, this is just a scalar. You can add very easily. So it will be 2 into that scalar equal to 0, and then you will be having A, B, C, D as 0, right? So which property I have applied here? Property 2. Yes, this is using the property 2. Okay. So Arpan is saying he got confused. See, T is this determinant, and then you just need to exchange this row with this row. If you exchange these two rows, then also this will remain same, but the sign will get changed, right? This will be minus T. And then if you add it, then the final quantity will be 0. This 2 into A, B, C, D equal to 0. Is this clear to everyone, or there is any confusion in this? Clear, right? Okay. See, these are very little things that I mean, whenever I think, see, I'm not sure, but this is my observation. I might be wrong. what I think that like coachings and all. I mean, okay, I do not know whether it is correct statement or wrong, but they make so much spoon feeding. Like we have to actually do it. Like we do not have any other option because we have to tell everything from the scratch, and we have to tell many things from the scratch, and everything we have to build step by step. That is good only. But I think side effect of that is that we do so much spoon feeding that you do not like to eat something by your own. Like if something is served to you, then your habit is like that it should be explained, otherwise you are not ready to accept it. I mean, you are not ready to apply your own brain. If something is there, like I might be wrong, but this is the side effect of the coaching. You might agree or disagree, I do not know, or maybe you are not in the current situation to analyze this situation. But anyway, like if you analyze this carefully, then because of the coachings, what happens that we think that everything should be explained. Okay, I mean, if something is given to us, then नहीं मैं ये नहीं समझूंगा, मुझे समझाओ. ठीक है, मुझे तो आदत है ना, मतलब मुझे तो हर चीज बहुत मतलब मुझे डिटेल चाहिए, डिटेल एक्सप्लेनेशन चाहिए. लाइक इन ग्रुप्स आल्सो आई सी दैट पीपल डू नॉट से दैट गिव मी एक्सप्लेनेशन, दे से दैट गिव मी डिटेल्ड एक्सप्लेनेशन. डिटेल से बिना भाई काम होगा ही नहीं मेरा, तो मुझे डिटेल ही चाहिए. ठीक है, तो मतलब दिस काइंड ऑफ स्पिन फीडिंग, दैट कैन लाइक दैट इज साइड इफेक्ट ऑफ कोचिंग, दैट आई थिंक. बट वंस यू गो टू आईआईटीज और आईएससीज, देन ऑब्वियसली लाइक योर मतलब दिस इज लाइक सारे सपने तुम्हारे टूटने वाले हैं वहां पे. दे विल नॉट एक्सप्लेन यू, आई मीन दे विल नॉट स्पून फीड you at least. Okay, they will explain you, but like let me tell you one situation. There was one subject that was computational mathematics and optimization, CMO, and that is like one of the heaviest in the mathematics in ISC, like one of the toughest. I don't know toughest or easy, I do not know, but it is mathematically heavy. This computational mathematics of optimization, this is prerequisite of ML. Okay, so that is taken by Chiru sir, and Chiru sir, I might have told you, he is the same who used to say that give me a symbol. Okay, so in that subject only he used to say that give me a symbol that is not written on the board. So in that subject, what used to happen that in the class we do not used to get anything. Like we almost everyone, like it's not me or my friends, almost everyone is almost blank, and maybe like we are just getting 20 to 30%. I think it is very high percentage. Maybe let me say 10 to 12%. Okay, we just get 10 to 12% of the things that like Chiru sir is teaching. And then after the class, what we used to do, we used to have a group study. In that like let's suppose this is a copy, this is equation 1. Okay, this is some equation that in the copy that is written. It is actually a true story, it's not any exaggeration, it is actually a true story. And let's suppose after this equation there is one line, equation 2, and in one page there might be like multiple such derivations, multiple such line in just one page. Then literally it happened many times that in a group study, that too with very good people. Obviously if people are from ISC, then they must be doing something, right? So I used to have a very good friend circle, but when we used to group study, then just understanding that how from this equation 1 this equation 2 is derived, sometimes literally I'm not exaggerating anything, sometimes it used to take more than 1 hour just to understand that. Okay, दैट कैसे ये क्वेश्चन आई, कैसे आई, फिर हम समझ रहे हैं, फिर एकदम से लाइक 15-20 मिनट बाद या आधे घंटे बाद एक बंदा बोलेगा कि ओ आई थिंक ये जो पिछले 3 पेज पहले जो ड्राइव किया था ना, वो सर ने यहाँ पे पुट किया है, और उसके बाद लाइक वी हैव कम टू दिस फॉर्मूला. So this kind of things will happen in ISC. Like they will not spoon feed you. They will give you this equation. They will give you this equation directly. I mean, you have to come up with this equation to in this equation. And in GATE, what used to happen? We give this equation, then we give at least 3 pages of explanation that how to come from this equation to this equation. Okay, so I mean that is okay. Like you will get to get used to of this in ISC or IITs, that when you go to the these places. Okay, so you were saying how you used to remember this in the exam. पता नहीं, बस पास हो जाते हैं जैसे तैसे करके. ठीक है, नहीं ऐसा नहीं है, मतलब एक बार शुरू शुरू में टफ लगती हैं चीजें, बट उसके बाद हो जाता है. मतलब पढ़ते हैं तो धीरे धीरे हो जाता है, कोई प्रॉब्लम नहीं होती. ठीक है. So I was saying this. ठीक है, ये समझ में आ गया ना सबको? Okay, tell me whether this is true or false. Now, in this, I'm saying that subtracting a multiple of one row from another row leaves a determinant of A or determinant unchanged, which means this determinant and this determinant are same. You need to use property 1, 2, 3 only. You do not need to use anything else. If this is true, then Y. If this is false, then Y. So what I'm saying is that if you have AB, C minus LA, right? CD and minus something maybe LA minus maybe LB, something like that. Suppose you have something like that. And they are saying that you can rewrite it in the same way, which is ABCD. Can you tell me how? Nikhil is saying use 3. Okay, 3 means linearity, which means I need to use linearity, which means let me just write it like this way, maybe. Yeah, Vani is also saying same. I think Yuvraj. Okay, so Karthik also saying same. Let me try linearity. Do you people mean this? Okay, then you take L or minus L common, right? Then you take minus L common from this. Can I do? Okay, let me go to the next page. Let me take minus L common. Okay, and we know we have just proved using property 1, 2, 3 only. We know that this is 0. How we have proved? Do anyone remember? Just now we have done it. We use the property 2. We have said like let's just exchange 2 rows and then we will get minus t and then all right. Then you know the whole story. Yes, Karthik, that is right. So this will be 0. That's what we have proved using property 1, 2, 3 only. Then finally you can prove that this is equal to this only. And have I used anything else other than property 1, 2, 3? Then no, right? Using property 1, 2, 3 only, you can prove that if you have something like this, then this is same as saying ABCD, which means that now I have a very powerful formula which says that you can apply Ri, you can replace any row Ri with Ri plus plus or minus does not matter. This L is constant plus K or L Rj. This is the very powerful derivation that we have done using property 1, 2, 3 only, right? Which means you can replace any row, this row with or this column, because row and column does not matter in case of determinant. Whatever you can do with the rows, you can also do with the columns, because the determinant of A and A transpose are actually same. We will talk about it later, but I mean, whatever you can do with the rows, that is also applicable for the columns in case of determinant. Okay, so Ri, that is you can replace this row with Ri, which means R2 you can replace with, here you have applied I think R2, that is getting replaced with R2 plus or R2 minus L R1, right? So that you can do, which means that will not change your determinant. But I just got a doubt where let's suppose this is ABCD. Suppose I multiply K in this. Let's suppose this is T. If I multiply K, then can I write this KT equal to AB KC KD? Right? And then that should be fine to everyone, right? And then I need to, let's suppose this is something I got, let's work with this. And let's suppose I just rewrite it this way. Maybe AB sorry, A minus, let me say KC, B minus KD. These two matrices are same, right? KC, KD. These two matrices are same, right? But if I'm applying this kind of thing, I mean in just 2 steps, after multiplying K, if I'm applying, then I started with T, but this finally I got KT. This is same as this, which is same as KT, right? See, what I'm saying is that I started with T, but if I'm applying this, that's the same thing, that instead of just 1 step, see, one idea was that if you have this ABCD, one idea was that you apply Ri or maybe R2 and you replace this R2 plus K R1, then you will be getting 1 second. I'm replacing this. No, I'm replacing R1 with let's suppose I'm doing this. That is allowed, right? Then I will be getting A minus KC or B minus KD, and then this is just C and D. Suppose. So these two matrices are same. I mean, this determinant and this determinant are same basically. Sorry, not matrices, determinants, right? But if I apply using two steps, which means I first multiply by K, maybe I apply using two steps, which is R2. First I multiply this R2 by K, KR2, and then if I apply maybe R1 should be replaced by R1 minus R2, then I get the same matrix. Sorry, not the same, not the matrix determinant. Then I'm basically getting KT. How that is happening? Is my confusion clear to everyone? Why that is happening? Nice. Yeah, this is happening because both determinants are not same. Because if you do like this, then finally you are getting this A minus KC, B minus KD, and this is KC KD. Okay, if you're doing the like in this two steps or something like this, then you are getting this, which is obviously the K times of this. I mean, these two are not same basically. The final results are not same. Then these two set of operations, which is like this, is not equivalent of saying that first multiply by K and then do this. Okay, these two are not same because this will leave your second row with multiple of K. Okay. Nikhil, is this clear now? What I'm saying, that if you apply directly, then you will be getting this. If you apply by these two steps, then you will be getting this. Okay. And then obviously these two are not same because this is a k times, like second row is K times of the first row. Anyway, like this just got, I mean, okay, I was not confused, to be honest. This was just a pre-planned that I will get confused. Then I will tell that I'm getting confused. Okay. So let's move further. Now tell me whether this is true. Yeah, so this is true. That's what we have just proved using property 1, 2, 3 only. Now quickly tell me whether this is true or false. If this is true, then how we can prove it using property 1, 2, 3 only. Just use property 1, 2, 3. So what I want to prove, that if you have one of the row or one of the column, okay, actually this row and column things does not matter in case of determinant, but yeah. So Yuvraj is saying swap rows. How that will be helpful? I'm not 100% sure. If I swap rows, take C, D common. No, if I take C common, acha, from the columns. No, let's not do with the columns, okay? I mean, let's just use a property 1, 2, 3 only. Because in the property 1, 2, 3, there is nothing about the columns, I think. I mean, if you want, you can do it. Maybe you can do it. But then also how to proceed further? Let's suppose you take C common from the first column, and then let's suppose you take D common from the second column. Then also, like, how it is making 0. Okay. Okay. Yeah. So there could be multiple ideas. So one of the ideas that Karthik has suggested is quite good. I mean, this is applicable. I'm not sure that he meant the same. Karthik and Nikhil has suggested that we can replace R1 with R1 plus R2, right? So here, from here, we will be getting this C, D. I mean, we can do this using property 1, 2, 3 only, C, D. And then we know that if two rows are equal, then the determinant is 0 using property 1, 2, 3 only, because that's what we have proved using property 1, 2, 3 only. So this is one of the proof that is perfectly fine. I mean, this is a good proof. Okay. Now let's just see if there is multiple proofs are possible. Maybe there is multiple proofs are possible. Let's see if there is anything. Let me just write this t into 0, or maybe 5 into 0 or something like that. Okay, let me write this 5 into 0. This is also 5 into 0. Then you take the 5 common and it will be 0 0 CD, which means you started with this matrix only. I mean, you started with 0 0 CD, and then that is equal to, you are just rewriting this 0 as 5 into 0, 5 into 0, and that is equal to 5 into the same matrix. So if this is t, then finally you have this t equal to 5t. That is possible only when t equal to 0, right? Which means the determinant is 0. Okay, so these are just some exercises that we can do. Otherwise, I mean, if you want, you can do this. Otherwise, leave it. C, Karthik is saying CD common then. Okay, anyway, so this is one of the way. This is, I think this is a good way. This is also a very good way. So you can do in any one of the way. Okay. Let's just see if that is true or false using property 1, 2, 3 only, which is saying determinant of the diagonal matrix is product of the diagonal elements. कार्तिक कोई प्रॉब्लम नहीं है ना वो, मतलब आप रिवाइंड करके देखना वीडियो, मतलब वो लाइक दिस इज नॉट इवन अ गुड मेथड, सो लेट्स लीव इट. ओके, कैन एनीवन सजेस्ट मी अ वे? टेक a11 a22, yeah. Okay, that is good. So Yuvraj is saying just take a11 common. Okay, so out of this, if this is a11 a22 and everything is 0, a33, these are zeros, then let's just take a11 common, a22 common, and a33 common. And then finally I will be having a11 into a22 into a33, and then 1 0 0 0 0 1 0 0 0 1, and then finally it is just a11 into a22 into a33. So which properties we have applied? I think property 3 from here to here, and then property 1, then property 1 from here to here, right? Property 3 is because we are taking common. Taking common is property 3. I mean, linearity is property 3. Anyone has suggested anything else? Okay. So, are there other possible variations? I mean, are there other possible proofs? I'm just thinking through it. Maybe. Not sure. I think this is a good way. So let's just stick to this. Okay. So now tell me if this is true or false. Determinant of upper or lower triangle matrix is product of diagonal elements, which means not just diagonal matrix. If you have a determinant of upper or lower triangular matrix, which means if you say that, let's suppose this is a lower triangle or upper triangle matrix, means like lower triangle means, sorry, upper triangle means that this diagonal element below the diagonal elements, the elements are zeros, and on the diagonal elements or above the diagonal elements could be anything. So if this is a22, let's suppose this is a33, then these are zeros. These three are definitely zeros. Other than this, other than these three, like the elements could be anything. Okay, so here this is a12, a13, a22, a33, a23, like that. So these elements that I have written a11 or like this, these could be anything, but the below the diagonal that must be zero, and this is called upper triangle. Okay, so how we can prove that is true or false? What we can do, we basically can apply the rule which is we have applied to make the elements as a pivot element. So okay, sorry, what we can do, we can make these elements as zeros, okay, without leaving this unchanged. Similarly, if this is 822, we can make these elements as zeros without making any change in 822, and then you can convert this matrix into a diagonal matrix. Okay, you can convert this matrix into a diagonal matrix. This will be a11, a22, a33, and these will be zeros only. 0 0 0. You can convert this matrix into a diagonal matrix using the formula that we have, which is Ri can be replaced by Ri plus Krj. Can you do this? I mean, I think we have already done this using when we have studied the reduced form, where we have went from lower to upper, right? So if you do this, then you will be getting a diagonal matrix, and finally you can say this is same as A11 into A22 into A33. So using just property 1, 2, 3, we can do this, right? Okay. Now let's just answer this. Suppose the determinant of A is 3, then what should be the determinant of B? Where B is just a in the last column, I think. Okay, let's take it for the granted that we can apply either to the row or to the columns. So in the last column, we are having 3 plus the this third column, right? 9, 12. Okay. See, I'm applying the C4 should be C4 plus 3 into C3. Why you people are giving me so complicated answers? 3 plus 3 into 3. How you're getting 3 plus 3 into 3? Okay. We can split, but for now, let's understand this way. You can go from here to here like this, right? And this is allowed. This will leave the determinant unchanged. So that is why determinant of B is also 3. Am I doing something wrong? This should be fine, right? Determinant. Okay, sorry, this is minus 3. Acha, sorry, we have also exchanged these two. Okay, so we have applied two things, C1 and C2 are exchanged. Okay, so if you do these two things, then the final answer will be minus 3. Because this will leave the determinant unchanged, this will make the determinant minus 3. Any confusion, anyone? Clear, right? Okay. Let's just solve this. Calculate these two determinants. So this is 2, 1. I think we have exchanged this third row is same. We have exchanged these two rows, I think. Then what should be the answer here? This is 2. Very good. What should be the answer here? This is A11, A12, A13. I think we have multiplied 2 here, and then we have done like this. Okay. It should be minus 4. Why? Because we have multiplied 2 here. So from here, we have said that 2 into C2. We have replaced C2 by 2 into C2. That is why the determinant will also get multiplied by 2. And then we have used this subtraction. That is okay. So answer is minus 4. Okay, everyone got it, right? Is there any confusion, anyone? Please let me know. Karthik, is this clear to you? Okay. I think Karthik is taking break. Okay, no problem. So what are the final answers? Yeah. Now tell me if this is true or false. Sorry, not true or false. What is the answer of this? This is 3. And then I think we have swapped it and multiplied, I think minus 6, something like that, right? Okay. That was easy. Okay. So let's solve this. Suppose that a matrix A is a 4 cross 4 matrix, and suppose the determinant of A is 11. If B is obtained A from A by interchanging row 2 and 4, then what is the determinant of B? It should be minus 11 if we are exchanging two rows. Okay. Therefore, determinant of A is minus 11. Now let's move to the next question. Suppose that A is 4 cross 4 matrix, and suppose that determinant of A is 11. Okay? Let A1, A2, A3 denote the rows of A, which means they are saying this is A1, A2, A3, A4. Okay? These are the rows of A. And B is obtained A by replacing A3 by 3A1 plus A3. Okay, tell me what should be the determinant of B? It should be unchanged, right? Because you are replacing A3 by A3 plus 3A1. That is okay. That is okay. That is why it should be 11 only. ठीक है, let's solve this. Now they are saying you are replacing a3, you are replacing a3 by 7a3 plus 3a1. Then what should be the answer? 0y, it should be 7 into 11, because basically you're first multiplying the 7. See, this, because of this 7, like you will multiply the determinant by the 7, and then because of this plus 3a1, this will not do anything. So basically whatever you are doing here, this is a1, a2, a3 and a4, and then what you are doing is that you are replacing this a3, let's suppose, with 7a3 first, and then you are getting this, which means you are getting this a1, a2, 7a3 and a4. This will make the determinant, I mean, if this is t, then your final answer, this is 70 obviously, and then you are replacing your a3, which is 7a3 already. Okay, maybe you want to call it a3 prime, and then you are replacing with something which is 3a1. Then it will not do anything. Then final answer is just 7 into the earlier answer, which is 70. Okay. Okay. Now, you can see here, if you want to see the solution, that is there. Okay. Now tell me this. Suppose that A is a 4 cross 4, and then they're saying B is obtained from A by replacing A3 by 4A1 plus 5A2. So they're replacing A3 by 4A1 plus 5A2. I mean, this is not the elementary row operation, that I completely agree, but they are replacing, which means if this is A1, A2, A3, A4, if this is A, and then they are saying there is a matrix B which is A1, A2, and then 4A1 plus 5A2. There is a matrix, okay, 4A1 plus 5A2, and then this is A4. Then what is the answer? Answer will be 0. Yeah. See, you have this sum, like let's suppose this is 11, determinant of this is 11. Let's suppose this is given to you. Then what you will do first, you will try to convert that to just look like A. Okay, which means you will say that, okay, this is 4A1. Let me just maybe apply A3. A3 should be replaced by, let's suppose, A3 minus 4A1, something like that. Then you will be having something like that. Maybe you will be having, after this operation, A1, A2, 5A2 and A4. And then you can replace, I mean, these are the rows, these are these are not the scalars, these are the row vectors. Okay, these are the vectors. And then this 5A2 and A2, you can take the 5 common, or whatever you want to do, you can take the 5 common, you can say that these two rows are same, that is why the determinant is 0. You're getting the point? If you, anyway, like if one of the row is a linear combination of other rows, if one of the row is linear combination of other rows, then also you can say determinant is 0. Okay. So Arpan is saying in the previous example, 7 was the multiple because the first element was changed. Yeah, so 7 was the multiple because I'm not applying Ri gives Ri plus KRJ. I'm not applying this. I'm applying Ri gives 7 Ri plus KRJ. So because of this 7, I got the 7 multiple. Okay. See, in earlier question, I was, see, what is the difference? In earlier question, I was replacing Ri with Ri plus something, KRJ, or maybe something like that, K1, K2. Okay. So this was the earlier question. Then in that question, after doing this, the final answer will be K1 into determinant of A. But if you do this, Ri, if you are replacing with something which is on the right hand side, you do not have Ri, maybe Rj plus Rk or something like that. Okay. Maybe any linear combination. Okay, then the final answer will be 0, because you're completely replacing Ri, and you're not even having Ri here. You're not having Ri here, which means you are saying that one of the row is a linear combination of this row and this row. That is why you are having a 0. Okay, why? Because you can say that if that is the case, then you can replace this row with, you can subtract the whatever the factor, you can subtract this a3 and then minus 4 r1 4 a1. That will not do anything to the determinant, and then finally you can say that the final answer is 0. Yeah, you can also split. Yes, that is also a good thing. So Anurag is saying we can also split. Let's suppose this is A1, this was A2. These are the rows, okay? And this was 4A1, 5A1 plus, or maybe 4A1 plus, what was that? 4A1 plus 5A2, right? 4A1 plus 5A2. 4A1 plus 5A2. And this is A4. These are the rows. So Anurag is saying that we can rewrite it like this. Maybe we can say that this is same as saying this is A1, this is A2, this is 4A1. Okay, these are basically rows. That's why I'm just writing like this. This is A4, and then plus this is again A1, this is A2. Tell me if this is fine to everyone. 5A2, this is A4. Is this fine to everyone? Yes. And then you can say you can take the 4 common because these are the determinant basically. Sorry, these are not the matrices. These are the determinants. Okay. You can take the 4 common, and then you can say that final answer will be 0 for both of them. So this is 0 and this is 0. This is 0, this is 0. Okay. Okay. Let's solve this. Whether this is true or false, they're saying that if you exchange these two rows and you multiply by -1, then both the determinants are same. These two columns. Is this true? Yes, this is true, right? Okay. Okay, you can do these exercises. These are easy ones only. Okay. Let me move further. Yeah, you can do these things. Okay. Now let's calculate the determinant of 2 by 2 using just property 1, 2, 3. Can you do this? Can you calculate the determinant of 2 by 2 using just property 1, 2, 3? Maybe let me help you. Let's just apply the linearity for the first row. You can say that, I mean, this kind of linearity will be useless if you have 0 0 CD plus A B C D. This kind of linearity will be just useless because you are ultimately having A B C D only. So this kind of linearity are not helpful. But let me apply the linearity where I will make one of the element as same. Maybe this is for the first row. The CD are the same, and then plus I can write maybe 0. CD are the same. Okay. Tell me the elements that I should be writing here. I think I can write 0 here and I can write B here. Okay. Okay. This is just a linearity on the first row. Now, maybe can you just give me the answer? I mean, can you just calculate the determinant using the property 1, 2, 3 only? Should I apply the linearity again on this? Maybe let me try doing this. Okay. So let's just apply the linearity again. Yeah, that is also fine, but let me apply the linearity here. Okay, so triangular matrices are also fine, but let me apply the linearity one more time. So here you will be getting A0 is same. For the CD, let me apply, maybe it is C0 plus A0 is same, and then this time it should be 0D. Okay. So this linearity is fine to everyone, I hope. And then let me apply linearity for the this determinant. Then you will say, then this is 0B, and then this row is same basically 0B, and then you will be having maybe C0 and 0D. Okay. Now since this is 0, so it won't survive. It will be just 0. And then since this is also, I mean, one column is 0, it is also 0. Then let's just see whether I can get something from these two. So this is definitely AD because this is a diagonal matrix. This is AD. Everyone knows this. And what is this? You can swap B and C, maybe the first row and second row, the first column and the second column. You can get minus BC from here. Right? You can swap the columns or the rows, and then you can get the answer, which is minus BC. So finally you will be getting AD minus BC. And have I applied anything other than property 1, 2, 3? Answer is no, right? We have applied only property 1, 2, 3. Here I have applied linearity. I think only property 3 was useful. Anyway, like property 2 was also useful. And maybe the property 1 was not useful here, but that is okay. Okay. So what we did, we basically just expanded it. And then like finally we got the 4 terms. I mean, initially 2 terms, and then we expanded it into, every term into 2 more terms. So basically just like a binary tree. I mean, we started with this, and then we expanded into 2 terms, and we got to know that, okay, let's just further divide into 2 terms, 2 more terms basically. I mean, we started with one thing, then 2 terms that we have divided, then each term we have divided into 2 more terms, each term we have divided into 2 more terms. Anyway, like we got the 4 final terms, right? But out of those 4 terms, only I think 2 terms got survived, right? I mean, 2 terms actually are not surviving, and 2 terms are just surviving, and then we are getting the final answer. Okay. Can we try this on 3 by 3, or it will be too much? Let's just try it on 3 by 3. Let's just see if we can get something from here. Okay. But before that, let me know if this 2 by 2 case is clear to everyone. Like we just applied the linearity, and then we further applied the linearity, and then finally we got the answer, which is AD minus BC. This hasn't survived. Okay. And then this hasn't survived. Only we got AD minus BC. Okay. Using just property 1, 2, 3. And now we are like, it took 1 hour, I agree, but we are on the verge of driving the formula. Okay. Okay. Let's just do it for 3 by 3, and then finally we will be having a formula for n by n. Maybe let me apply the linearity. Let me just say that these 2 rows are same. At least these 2 rows are same. Okay. Maybe I can have, I think, the 3 terms like this. I know you people think that I do copy paste a lot. Okay. And Deepak doesn't do that much copy paste. He write everything. If he need to write, then he will just write again and again. But yeah, this is my nature. Okay. I'm a bit lazy, and Deepak is a bit active, but that is okay. 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 So here maybe you can say this is 0. Arnav is saying IT sector effect. This is 0. This is A12. This is A13. And definitely I can have A11 here. And then maybe I can have 0 here, A13 here, and I think 0 here, and okay, A12 I have. Okay, let me take 0 only. Okay? I mean, at one of the place, I just want one thing. Okay, 0. I don't know. Maybe let me take this also 0. Actually, let me do very systematically. Let me take one of them as 0. A11, and these things are 0. This A2, A12, this is 0. A13. Huh. Yeah. So that is fine, right? Okay. Okay. Now, I hope that is fine to everyone. Now, what you can do, I mean, we started with 1 determinant, and we just have 3 determinants in our hand. Then we can further split. We can further split this into 3 more determinants probably. Okay. Okay, some jokes are going on. Nikhil is saying that Microsoft can just eliminate the competition if they disable Control C, Control V. Karthik is saying, okay, we will move to Linux or Unix. ठीक है तो ठीक है so now what we can do, we can further divide this into maybe 3 more, and where like for now I just focused on one first row, then I can just focus on the second row. Okay. And maybe I will just keep the third row and first row as it is, which means I can just focus on the second row, where I will just say probably this is A1100, and then this is also A1100, and also third row is also same 311 322 3 A33 जो भी है ठीक है, A31, A32, A33 plus third term which is A1100, and then this is again A31, A32, A33. ठीक है. Now in the middle, what you will be having? You will be having maybe A2100, 0, A220, 00, A33. ठीक है. Is this okay to everyone? Okay. Now you will be doing the same with this particular determinant, and then same with this particular determinant where you will just operate on the second row, and then again maybe again you can divide this into three more parts where you will keep these two rows as same, and then you will be just operating on the third row. Maybe let me quickly do it. Okay, just one last time. Let's just do it. No, I want to conclude something from here. That is why I'm doing. Okay. Now, if you divide this further into maybe three parts, where you will be having this particular row is the same, this particular matrix. Okay. So now you will be having this as 0. Oh, sorry, let me go systematically. 3100 A32 0 A33. Okay. And then probably you can do same for this, like this. ठीक है ना? So finally, what you will be doing, you will be basically ending up with these kind of matrices where in just one row you have one element. Okay, in one row you just have one element, everything else is zero. Because if there were two elements, I have applied linearity on the rows. If there were two elements, I have just split that into two parts. Okay. So how many total, how many determinants will be at the last level? Ultimately, see, you started with one, then from this one, you will go to these kind of three. Okay, and then from this you will go to the like one more level, and then one more level, and then you will stop at this point. So 3 square 3 power 3, which means 3 power 3 is 27, right? 27. So ultimately these are the sum of 27 determinants. This determinant is just a sum of 27 determinants. Okay. I mean, these intermediate determinants are not useful for us. We have just split the determinant into 27 plus. Now you notice one thing, that every of this determinant type will be having one element in one row. Okay, just one element in one row. Why? Because if there were at all multiple elements, like this, then I have splitted that into two parts. Okay, so this must be having one element in just one row in the last level. Everyone agree with me? See, if there were multiple elements in just one row, I will apply linearity here. After this, after first level of linearity, I just get one element in first row. In first row, there are no multiple elements, right? Okay? And then I kept the first row same. Then I divided the second row into three parts such that I get one element in the second row, one element just in the second row. And then at this level, there are only one element in first two rows. And then next, I have just one element in all of these three rows. So here, whatever kind of matrices I have, or whatever kind of determinants I have, every determinant will be having just one element in the one row. One element in just one row. Every determinant will be having the same, like this story. Okay. So basically, you started with this A11. Okay. You started with this kind of a determinant. And then you are having 27 determinants. Okay. How you are getting 27 determinants? Basically, you are saying that at every one place, there are how many entries? There are 1, 2, 3, 4, 5, 6, 7, 8, 9 entries, right? Okay. From here directly, how can I say that we will be getting 27 matrices? Nikhil is saying, are we not counting linear internal matrices? No, internal matrices are not useful. Okay, why there are useful, like ultimately you will be getting the summation. This matrix is a summation of these 27 determinants. Okay, you have just further split that into two parts. You are not summing everything. I mean, why will you sum everything, right? You are just splitting that into two parts, further splitting, and then everything is in the plus. Okay. So you are having 3 power 3, which is 27 determinants, where every row is having just one element. Now, why we are getting 27? Can anyone tell me? Yeah. So Ekta is saying for every row we are getting 3 splits. So here we will be having 3, 3, 3. Okay. But some more, I mean, some more. I mean, this is a valid argument, but some more intuitive argument. Can anyone give me? You people are doing combinatorics since a long time. I mean, I am also not sure that how to give something valid. I have not thought about it. Let me just think. You people also think. Let's just spend 1-2 minutes maybe in this. Okay. So I want one element in just one row. One element in one row. Yeah. Each row has 3 choices. Yeah, that is right. I think that is right. So basically, I will keep each row is having the 3 choices. Basically, I will keep A11 here, or A12 here, or A13 here, right? And similarly here, like the total number of determinants that I can generate such that every row is just having one element. Then it will be 3 power 3, because I can have A11 here. Everything else should be 0. This is one of the possibility. In the second row also, I have 3 choices. I will take A22 maybe. This is zeros. I will take one more like A31, and this is zeros. This is one of the possibility. Okay, one of the possibility. Do you all agree with this? This is just one of the possibility. Similarly, there are remaining many other possibilities where you will say that maybe you can take maybe A11 from the first row, maybe A12 from the second row, maybe sorry, A21, right? A31 from the third row. This is another possibility. Basically, and each row you just take one element. So there are 3 choices. Okay, there are 3 choices for each row. Each row has the 3 choices that which element is to present. Let me write the same statement that Yuvraj is saying. Each row has 3 choices that which element is present. Everyone agree with this? So that is why you have 27 choices. Okay. Do you people think I'm going so slow? I mean, like I just realized that I'm going so slow, but I'm just adopting this kind of teaching where I do not want to rush anything. I just want to go slowly. I just want to let you digest the things that I'm teaching. Okay, and along the way, I also want to think through during the lecture that what is happening. Okay. So everyone agree with this, right? That each row is having the 3 choices. Maybe you can have A11 here. Maybe you can have one of the element as non-zero, one of the element as non-zero. This is one choice. This is another choice. You can have any other choice. Maybe you can have, maybe you can say that, okay, in this row, I kept this as non-zero. In this row, I kept this as maybe non-zero, 2, 1, okay. And maybe in this row, I kept this as non-zero, maybe like this, okay. This is another possibility. Okay. Okay. Now, can you tell me, out of all those 27 possibilities that I have, how many possibilities will survive? See, let me go back to this 2 by 2 example. Here I have each row, since each row is having just a 2 possibilities. So I mean, either you keep A, maybe you keep A, and then you keep this thing at 0. In this, maybe you keep B, this thing at 0. And then in the first row, maybe you keep A, this thing at 0. In this, maybe you can keep, sorry, this is C. Maybe you can keep D as non-zero, like that, right? So you will be having 4 determinants, and then finally, I think 2 are not surviving, 2 are surviving. right? Now here, how many of them will get survived? See, this kind of things will not survive, I'm sure about it. But how to count this? 18, 3, 9, okay. I'm okay. I never thought that this will be like I will be doing combinatorics in linear algebra. But I think actually, to be honest, I have also not done the calculation. I know the answer, but I have not done the calculation. Okay. Yuvraj is saying inclusion, exclusion. Nikhil, 18 will survive. Answer I know. Answer is not 9. Answer is not 18. Okay. Answer I know. We just need to, I will not tell you the answer. It is not 9. It is not 18. It is not 24. These are wrong. Okay. Answer I know. And maybe I can tell you the answer. Yeah. Nikhil is right. Answer is 6. Answer is 6. We just need to think about it, that how we are getting this 6. Okay, 6 is the correct answer, that only 6 combinations will survive out of those 27 combinations. Let's just think about it, that why only 6 will survive. I think anyone which is having all zeros in the rows or all zeros in the columns will not survive. Or maybe let me think in opposite way. Like what will survive is that if at least one of them is non-zero, right? I mean, what will survive, that I know that if at least one of them is non-zero, then it will survive. Let me think in that way, maybe. Okay. So let me say that if in any row or column we have at least one non-zero, then that determinant will survive. Kushal is saying each column contains only one element plus each row contains only one element. Yeah, that's very nice. So final answer is this. But how to come up with that kind of intuition? Let's just try to build it. So Yuvraj is saying अगर A11 है तो A2 वाले में 1 नहीं आएगा. Yes, that's very nice. Okay. So we have got the answers. Let's just see if we can also do it. I mean, Yuvraj and Kushal got the answers, but let's just see if we can also solve it. So if we have at least one non-zero, that determinant will survive. So for this first row, okay, for this first row, I will be having 3 choices. Maybe I can have A11 as non-zero, A12 as a non-zero, A13 as a non-zero. Any one of them as non-zero. But for the second row, do I have 3 choices? See, let's suppose that I pick, maybe let's suppose I pick A11 as non-zero. Okay. Let's suppose I say that A11 is non-zero from the first row. From the first row, I choose A11, or I can choose A12 or like that. Okay. Maybe I can choose A12 in other possibilities. Maybe it is 0, A12, 0, like that. Okay. Let's not worry about it. Let's just focus on one thing. So here I'm just saying that if A11 is non-zero, then here, can I take this as non-zero? Because in each row, I'm just taking one as non-zero. If I take this as non-zero, then this will definitely be 0. This will definitely 0. Okay. And if I take, let's suppose in whatever I do, I cannot, it is just a TikTok, right? TikTok nahi, sorry, क्या नाम है उसका? वो, I forgot that game. 0x वाला कौन सा गेम है वो? I mean, game है. Tic-tac-toe, हाँ, tic-tac-toe. So it is just like that. I mean, if you have these 2 columns as zeros, okay, you cannot make both of them as non-zero. By like in the third row, you cannot pick a non-zero that can make both of the columns as non-zero, because one of the column has to be 0. That will not survive. So if you are taking this as non-zero, like after this A11, if you're taking this as non-zero, things will go wrong, because then these have to be zeros, and now you cannot save yourself. That will not survive for sure. Okay, so here you do not have 3 choices. Here you have 2 choices only. Maybe you can take this as non-zero, or you can take this as non-zero. You cannot take this as non-zero. Is this clear to everyone? Because if you take this as non-zero, then that term will not survive for sure. Okay. So you will be taking this as non-zero or this as non-zero. Basically, you have two choices here. Okay, let's take any one of them. So here you had three choices. Here you have whatever you pick. Okay, and then you have just two choices here. Let's suppose you pick non-zero here. Okay, then this will be zero. This will be zero. Then here again, how many choices you have to save yourself? See, if you do non-zero here, then it will be zero here or here. You just have one choice, right? You just have one choice. You just have one choice. You need to make this as non-zero. So just one choice. So there are only 6 choices that you have to make any column or any row as non-zero. So basically, you need to pick only 3 elements, right? I mean, in every determinant of these kind, there are only 3 non-zeros. So, and there are entries like this. So if there are 3 non-zeros, you have to go diagonally, which means if you are taking this as non-zero, since there are only three non-zeros that you have to fill this nine blanks, and there are only 3 non-zero, then you can make like this, or maybe let's suppose, see, there are 9 places, then you can go like this to make non-zero. You can probably this is 0, let's suppose, you can probably go like this. I mean, in one row or one column, there will be just one element which is non-zero. Okay, or maybe you can go like this. Yes, Asus, there is 3 factorial. How you come with this 3 factorial thing? You can go like this also. Maybe you can take this as non-zero, then this is non-zero. In one row and one column, as Kushal is saying, that in one row and one column, you will be having just one non-zero. Right? If we are having 2 non-zeros in just one row or one column, then this will be a problem to you. Why? Because whatever you do in the third row, one of the column will be 0 only. Maybe if you are doing this as non-zero, then this column will be 0, right? Whatever you do. So basically, you have just 6 choices. Basically, you will always be having only 3 factorial choices. I mean, in case of 3 cross 3. So in case of n cross n, if I expand, if we expand n cross n, then we will get n factorial. No, there is no m or n. Ekta, there is only square matrices. Okay, there are only square matrices. So if we expand n cross n, then there will be only n factorial terms will survive. Which means if you open up any determinant of n cross n, then in the answer there will be n factorial terms. See, in case of 2 cross 2, in case of 2 cross 2, there was 4 terms, I think, right? Sorry, this is 2 cross 2. Sorry, this is 2 factorial, right? 2 factorial, just 2 into 1. Okay, so there are 2 terms. Why? Because there are 2 factorial terms. Similarly, if you expand this 3 cross 3, then there might be 27 terms or whatever. Ultimately, only n factorial, 3 factorial, which is 6 terms will survive. Okay, if you know the determinant already, then I can tell you. See, one term will be a11. Let me expand it. One term will be a11 into a22 into a33 minus a32 into a23, like that, right? Corresponding to a11, there will be 2 terms. Similarly, corresponding to a12, there will be 2 terms. Similarly, corresponding to a13, there will be 2 terms. So finally, there will be just 6 terms. Plus minus we will handle later, but finally there will be 6 terms only. Okay, in the determinant. And then we have our formula. Basically, using just property 1, 2, 3, we got the formula because we just expanded it so much such that ultimately only one row is having only one element. And then we come up with the conclusion, not just one row with one element, one row and one column with one element will survive. I mean, ultimately, using the linearity, we came up with this, which is basically one row is having one element. That I agree. Then all will not survive. Out of these, one row and one column, one element will survive. Right? You all agree? So, which means there are 6 terms which will survive. Okay. Yeah. So now let's just maybe let me try more general formula. So what I will say that let's suppose this is A11, A12, A13, this is A21, A22, A23, A31, A32, A33. Okay. Okay, so now you might be saying that you have just, like some people are saying this is awesome derivation, great derivation, but some people might be thinking that I'm wasting time. But don't worry, like whatever we will be teaching you, it will be helpful in one way or another. Either it will be helpful in your combinatorics, it will be helpful in the linear algebra, it will definitely be helpful. Okay. Ultimately, whatever I'm teaching in linear algebra, that is going to help you in the interview for sure. See, for other computer science subjects, which are operating systems, compiler design, C programming, data structure, or digital logic, or whatever, for other computer science subjects, we already explained in very much detail. And if you appear for the interview, then you have the choice. I think I already told you in the interviews, you have the choice to appear for the there are like already three pools for the pool A, pool B, pool C. Pool A is theory pool, where you will be having subjects like maybe graph theory, theory of computation, okay, graph theory, maybe TOC, like that. Algorithms. These are theory pool. And then in pool B, system pool will be there, which means OS, compiler design, and DBMS. These kind of things will be there. And in pool C, intelligence pool will be there, LA Pro. Okay. So if you choose to appear for the interview, you have the choice. In case of research interview or the RA interviews, you have the choice. If you choose to appear for pool B or pool A or pool B, then you already know the things very well, because we will be teaching like we have taught whatever subject we are teaching, we are teaching to our best knowledge. Okay, you already know these things. But suppose that your interest is in machine learning, and if you want to appear for this, then it is better to maybe spend one or at max two more classes to understand LA or Probe better, so that in the interviews you will not face any problem. Okay. So for pool A and pool B, we are already covering, but for pool C, we are covering through linear algebra and probability, because that's the only thing that they will ask you. They will be asking you. Okay. Now, Nikhil is saying that pool D will be like there are three pools, but pool D is like sir le lo Bhagwan ke naam pe. Okay. So I said here 6 terms will be surviving. Now let me probably write those 6 terms. Okay. Let me quickly do it. Maybe here I'm just making one of them as in one row and one column I will just make one non-zero. Okay. You can take anything, but yeah, this is one of the term. Second term will be maybe you can say like this A23. Okay. I think ऐसे तो I need more space. Okay. So second term will look like this, which is maybe do I have multiple choices here for a like this last row, or there's just one choice, right? There's just one choice. I think this is A320 plus there will be a third choice which will be maybe this is, let me pick okay, this A11 is done. Maybe 0 A120 like this. Maybe here let me pick some non-zero, and let me pick the non-zero here. Okay, 3 and then similarly there will be 3 more terms, right? So there are terms like this. Now can you give me the formula directly? Now this will be A11 into A12 into A22 into A33. Now can you tell me what is the determinant of this? What is the determinant of this? You just exchange these 2 rows and make it diagonal. Just try to make it diagonal. Okay, just using the property 1, 2 and 3 only. Just exchange these 2 rows and try to make it diagonal. It will be A11. If you exchange, it will be minus, obviously, A11, A23, A32. Okay, and then if you exchange maybe if you exchange these 2 rows, then it will be minus also. This is A12, A21, A33, like that, right? So there will be actually 3 plus and 3 minus. Okay. So I have not written all the terms, but there will be 3 plus and 3 minus. Okay. So just observe one thing here, like there will be 6 terms. I'm just writing 3 terms, but yeah, there will be 6 terms. You can try writing those 6 terms. Just observe one thing here. In the first row, I'm taking A11. In here, I'm taking A12. Basically, here I'm taking the first row number is same. The first row, second row, see, the first index will be same always, which is the first row, second row, third row. And then in the first row, what you are choosing is first element. In the second row, what you are choosing is second element. Third row, what you are choosing is third element. Okay. Here, this is first row. The first index will be same. The first row you are choosing first element, second row third element, third row second element, like that. In the first row second element, second row first element, third row third element. Okay. So basically, the first index will be same. The second index is just a permutation of 1, 2, 3. Okay, maybe 1, 2, 3, maybe 1, 3, 2, maybe 2, 3, 1. And how many permutations are possible? For this 1, 2, 3, how many permutations are possible? These are three factorial permutations, which are 6 permutations. That is why you have 6 answers. Okay, which means the first index is fixed, and then you have permutation of 1, 2, 3. Okay, I hope everyone understood till this point. Now, suppose I ask you that like I do not want you to drive that much. I just ask you that what is the sign of this particular term, plus or minus? Plus. Why? Because what you will do, you will probably draw the matrix corresponding to it. You will say you are taking this element, you are taking this element, you are taking this element. So you do not need any row swap or column swap. So that's why the answer is plus. What is the sign of this? First row you are taking first, second row you are taking third. Okay, you are taking this. So this is the thing. Then finally, I think the answer should be minus, because maybe you need to swap these two, right? That is why the answer should be minus. Okay. 1 second. Can you tell me this answer? What should be the answer of this? Anyone? Okay, so you are getting in the first row, everyone solve it. In the first row, there are actually 4 possibilities, like 1, 2, 3, 4. Okay. So there are 4 by 4. Okay. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So in the first row, you are taking third. Maybe this is non-zero. Okay. This is non-zero. And second row, second, this is non-zero. Third row, fourth, this is non-zero. Fourth row, 1, this is non-zero. Okay. Now you need to tell me the sign. Maybe you can swap this with this. I think only one swap. No, the 2 swaps are required. I think maybe first you can swap these 2 so that you can have this fourth at the end. Maybe, right? First you can swap these 2 so that fourth at the end, and then you can swap this third. I mean, once you swap these 2, I hope you got it right. The answer will be plus, because there are 2 swaps required. Okay, everyone got it? First we will swap these 2, and then whatever we are getting will be something like this. Will be here you have non-zero, and here you have non-zero. This is 0, 0, 0, and then you have this is 0, this is non-zero, 0, 0, this is, and then you can swap these 2. Okay, so finally 2 swaps are required. That is why the answer is positive. Okay, everyone understood this? Basically, what is happening is that if, like, you just need to check that if that is, let's suppose you just take the last indexes, that is 3, 2, 4, 1, 4, 1. Okay, you convert this 3, 2, 4, 1 into 1, 2, 3, 4. How many steps are required just to convert this 3, 2, 4, 1 into 1, 2, 3, 4? That's what we are doing. So you just swap this, maybe this is one swap. Okay, and then maybe you swap these 2. Okay, this is one of the possible way. Then you have 1, 2, 3, 4. So 2 steps are required. I mean, given this, these are the last indexes, because first index is fixed. You are taking something from the first row, something from the second row, something from the third row, something from the fourth row. So the first index will always be the 1, 2, 3, 4, like that only. First index will be 1, 2, 3, 4, like that only. Thus, based on the second index, you are having plus sign or minus sign. Okay. Yeah, Arnav, thank you. So Arnav is saying this intuition would not have developed if you did not explain the how formula came. Yeah, right. So actually, these kind of things are helpful in the interview. That's why I do not want to leave any stone unturned. So that yeah, inversion counter is very good example. I was just about to say that. Okay. So that in the interview, like I mean, if they ask these, actually they ask these kind of things, and like let me tell you honestly, you might not, I mean, you will believe me, but you might not feel that thing. So there was a student, and the student name was Abhishek Solanki, I think. I'm not sure if I should tell this story in the class because it is recording, like it is getting recorded. But okay, that is okay. So basically, he has watched our engineering mathematics lectures, all linear algebra, probability, calculus, everything, and then he has went to ISC and IIT Delhi interviews. Okay, he told me that he was like exact line, okay, exact line. He told me that professor was surprised by his knowledge. Okay, I will tell you the real story. So he was okay, he was actually not filling the ISC form because his rank was, I think, 150 or 158 or something, 150, 149, I think. Okay, 149. So his rank was 149, and he was thinking that he will not get the ISC because under 149 maybe he will not get it. So and he was not sure about the ISC, like he should be going to the ISC or not, and he just filled the ISC form because I asked him to fill because like you should be filling the forms at least, right? And then I told him to just watch our engineering mathematics lectures. If at all there will be interview, then you should be able to clear the interview. So he told me that in the interview he was so confident. He took, I mean, the professor gave him the chalk, and there was a blackboard. He took the chalk and he was so confident while explaining the linear algebra and probability concepts that professor was just impressed that how can someone be so confident. Okay, he told me that I'm not sure about you guys, like for the linear algebra, if you're making notes, then how many pages you have filled till now? So he told me that almost, the one copy or one of his copy got filled by all the lectures, like after the linear algebra, and he made a proper notes and everything. He has just understand very well. And in ISC and IIT Delhi, both interviews, professors were very impressed just by the linear algebra probability concept. So that's why I'm explaining the concepts in the detail that I also explained last year, so that in the interviews, at least, like if we spend maybe, let's suppose, okay, at max we are spending, let's suppose, 8 hours in including probability and linear algebra, extra 8 hours. Okay, extra, I'm saying extra 8 hours that I should not be spending. Probably if I just tell you the formula, if I just tell you everything directly, then I could have saved these 8 hours. But this will not be helpful. I mean, if I save those 8 hours, you will cry after the gate if you get the interview calls, and then probably you will not be able to clear if I do not tell the intuition behind everything. Okay, because in the interview they are not interested in the formulas, they are interested in that how we are driving these things, right? ठीक है, ये सबको समझ में आ गया ना कि how we are coming up with the sign. Okay, now are we ready for the formula? I think we are ready, right? So let me write the formula for n cross n finally. The formula for n cross n that took almost more than 1 hour, that is basically, you will say summation of all permutations of a1, maybe alpha, a2 beta, like that, a3 gamma, an, maybe omega, something like that. Basically it will be, I mean, it will, like, sign will be plus minus depending on the permutation. So you will take all the permutations of this 1 2 3 4 or till n, and you will be like, one of the permutation is 1 2 3, maybe 5 4. Okay, for the 5 terms. So one of the term will be a11, a2, no, a22, a33, a4 5, a54, like that. I mean, this 1 2 3 4 will take on the place of alpha, beta, gamma, like that. Okay, so basically one of the permutation will be this. You will be taking all the permutation of the second indexes, and you will be having plus minus based on that, and this is the formula. How many terms are there? These are the n factorial terms. Okay, okay. So this is one of the formula, but we have other usual formula also. For that I will talk about in just a minute. So this formula in the Gilbert string, that is called the big formula. Okay, they have called it a big formula. I mean, I'm just copying everything from the Gilbert-Stein. So I have watched those lectures many times. So I just whatever I teach is directly from the Gilbert-Stein. Okay, either from his lectures or from his books. So they call it big formula in the book. So I'm just telling it that this is a formula that we have. Okay. Now let's just find the determinant of this particular matrix using the formula that we have just derived. Okay, should we take a break for now? Okay, so let's take a break and we will be continuing at 9:30.